Generators Revisited. The figure shows a single metal loop being rotated at a constant angular speed, omega, in a uniform magnetic field B. Note that the direction of the loop's area vector A is perpendicular to the plane of the loop. Which picture shows the least magnetic flux? Well, that's going to be figure 3, isn't it? Because in that case, the magnetic field lines are simply scraping the surface. They're not piercing the surface. Which one has the most? Well, that's going to be number 1. What's theta for picture number 1? Well, for picture number 1, theta is 0 degrees. And for picture number 3, it's 90 degrees. And whenever we are finding magnetic flux, you might remember that one equation for finding magnetic flux is that it's B dot dA. And whenever you take a dot product and the angle is 90, you get nothing. And whenever you take a dot product and the angle is 0, that's when you get a maximum magnitude. Letter C. Write the vector equation for magnetic flux whenever the B field is constant. Whenever the B field is constant, the magnetic flux is written like that. Letter D, write a new equation for magnetic flux. Let's eliminate the vectors and put a trig function in there. The magnitude of the flux is going to be B times A. And then how do we remember which trig function it is? It's the trig function that doesn't have the same letter as that process right there. So this is a dot product or a scalar product, and the trig function that doesn't start with S, that's the cosine. The trick works for cross product as well. For cross product, which starts with a C, it's the trig function that doesn't start with a C. It's the sine. That's how I remember it. Letter E, modify part D, taking into account angular displacement equals angular velocity multiplied by time. Well, we could rewrite this then. Angular displacement is equal to angular velocity times time. Letter F. Recall that one formulation of Faraday's law for when we have multiple loops is this right here. The negative sign, you remember, is essentially Lenz's law, which tells us the direction of this induced EMF. By combining this with the part E answer, derive an expression for the induced voltage for the case at the top of the page, namely when we spin loops of wire of a given loop area in a uniform magnetic field at a constant rate of spinning. If we take the derivative of this right here, what do we get if we take the time derivative of that? Whenever you have a derivative, you can keep the constants right where they are. Then when you differentiate the cosine, you get negative sine of that thing. But then you have to use the chain rule, and you have to take the derivative of the thing in parentheses, so that's omega. I think what we are after here, we are looking for the induced voltage, and that is the induced voltage. Again, you could leave the negative sign off if you wanted. It talks about the direction, so I think I'm going to do that. And since we have n loops here, we have a multiple of n that gets put in here. This is kind of a nice way to remember this. That almost looks like a W, WNBA. So that's the magnitude of the induced EMF. Based on part H, what are the 4 variables that can be increased in order to maximize the induced voltage? The maximum that a sine of something can have is just 1. So as these things get bigger, the induced voltage will get bigger. Omega n B A. And let's write what those are. Angular speed, in other words, how fast we spin the loop, and that's in radians per second, isn't it? The number of loops that we have. That's going to make a difference. That's the B field strength, which is in Teslas. And then the area of the loops, which is in square meters. You got a strong magnetic field, you got a big loop, you got lots of loops, you spin it real fast, you're going to get a big induced voltage. Last couple of questions here. Which variable from part G is depicted differently at right compared to the figure at the top of the page? Well, the figure at the top of the page looked like this, right there. What's different? N is different. How much more difficult is it to spin these guys compared to if there's only one loop?